Alright, last time we looked at movement in one direction. Either east, either north, south, away from or towards a wall. We were looking at just one direction. Today, we're going to complicate it just a little bit here. So let's say I'm in my hypothetical house, Casa del Ease, and I decide I'm going to go for a run. So I'm in my house, I get ready, I stretch, I warm up, I do high knees, and then I decide, okay, I'm ready. So I walk out to the sidewalk, and I'm like, okay, I'm going to start my run. So from this starting point, I'm going to even say that starting point, x position is equal, okay? And I'm going to run due east. We're going to run due east for about 2,200 meters. Keeping it in meters for physics, we're going to keep it in standard. Or, not standard, we're going to use it in metric, right? At this point, though, my road dead ends, and it takes a 90-degree turn north, and I'm continuing to jog. I'm going to say that I go north for about 1,100 meters. I can make that point a little bit better. 1,100 meters. All right. We're going to say during the x portion, during the east portion of my run, so I'm running that way, add an arrow to indicate that's the direction I was running here. We're going to say that that took me roughly 10 minutes. However, I want to know my velocity in meters per second. So to do that, I'm just going to take 10 minutes, convert that into seconds. We're going to do some unit analysis here. And I need minutes on bottom to cancel it out. Now I would ask how many seconds are in a minute, and you would all say 60 seconds. Okay? My minutes. So unit analysis means the label, the unit that we have in our numbers, they can cancel out. If there's one on top here, one on the bottom, they cancel. So in this case, I have 10 times 60. That should be 600 seconds. All right, so just kind of practicing unit analysis there. It is really important. So that's kind of my x, how long it took me to go in the east direction, I should say. But then I turned north. I didn't keep going straight. I didn't keep going in that one direction. I've added a second dimension to my change in position. I'm no longer changing my position along the x-axis. I'm now changing it along a y-axis. So we're even going to come back here. We're going to say that my starting y value is 0 as well. Now those values, really can be anything, so long as they're on a reference frame. If you're doing it on graph paper, you could have your starting and ending positions wherever you want them to be. I'm just going to say my starting positions 0 for x and 0 for y. So then my y was 0 this entire time along this axis. I don't know why that's there. We're going to say, though, that this is a 90-degree angle. Once I turned north, so we can even come in here and say north is positive, east is positive as well. That way it's just we're also specifying our positive and negative values. So once I did my 90-degree turn to go north, so I'll even put an arrow to indicate that's the direction we were running, my x value is not changing, but my y value is now. So I'm in South Dakota. I'm going to say that I went for this jog in late September, so we have those northerly winds, winds from the north really pushing against me, and we're going to say that this direction took me 7 minutes. Or if I wanted to go through this whole thing again, I could go 7 minutes times 60 seconds per 1 minute. Minutes cancel, but 7 times 6 is 42. Add another 0 at the end. It took me 420 seconds to move north. So now I can look at my change in my x position and my change in the y position. I can't do these both at the same time. I can't add these up. I could do that if I was looking for average speed. Speed does not care about direction. Velocity, though, does. In velocity, once again, I'm going to keep stressing this point for a good month or so. Direction's really important. Velocity matters more than speed does. So I would need to figure out my velocity in the x direction and my velocity in the y direction. So last time we learned, when we talked about velocity, I said v equals our change in position, or x, over time, which is going to work really good for our velocity in the x direction. It's going to be our change in our position along the x-axis over time. For vy, it's pretty much the same thing, except we're looking at the change in our y position over time. So in this case, for vx, we're going to have our x position changed by 2,200 meters, or 2,200 meters. That part of our journey took 600 seconds. We'll come back to our math here in a second. Our velocity in the y direction, though, our change in y value here was 1,100 meters. And we said that took 420 seconds. All right, so now let's go through. Let's figure out what is our velocity in the x direction. So let me get out calculator here. So we have 2,200 divided by 600. So in that case, we're going to round that to one decimal here. Once again, we're going to save significant figures for later. And we're going to say that took 3.7. If I look at my units here, meters on top, seconds on the bottom, my velocity is in meters per second. Okay, that's my Vx. Our Vy, on the other hand, is 1,100 meters divided by 420 seconds. In this case, once again, one decimal again, we're going to go with 2.6. And once again, meters per second. All right, they're both velocities. They both have the same unit, meters per second, but it's going to be important that we say the v of x is 3.7, or v of y, or velocity of y, is 2.6. They're same units, numbers are pretty similar, but they're in different directions. So now I can even go through, and let's plot some of this stuff here. So let's go, we're going to go red. So Vx, so now we're going to go into the difference between what are called scalar units and what are called vector units. Scalar units are just numbers. They just signify quantities. How many apples do you have? 8. How many students are in the room? Probably 20-something. Those are numbers. You know, most things in life, we just care about the number. That's what speed is. Speed doesn't care, you know, it's just a number. Vector units, though, have a specific direction. They're a quantity in a specific direction. That would be things like, so I could talk about how fast is the car going. Typically, that's just speed. I'm not going to care too much about, you know, what direction that car is going. But if I asked, how fast is that car coming at me? Now at me is a direction. I'm working with a vector unit. Now I really, really very much care about the vector value for that. So with that, we can actually plot these things, these values, you know, kind of on a grid, you know, on graph paper if I wanted to. The 3.7 meters per second, we said that was in the easterly direction, that positive direction. So I can come through and say, that's 3.7 meters per second. Where vector quantities get really useful is I can actually add vectors together, even if they're not going along the same direction. And to do so, I'm just going to take my vectors and plot them kind of head to tail. So I could have started with the y vector. I start with x. This works either way though. So now when I go through to do my y value, and we're gonna go blue for this one. The y value we said was 2.6 meters direct. So after I got done with my x part, I then did a 90-degree turn, and my y value here was 2.6 meters per second. So now, with these things plotted head to tail, my actual total velocity, the sum of my two velocities, the sum of my two vectors, I can figure that out just by starting with my first starting point and drawing an arrow that ends at my last arrow. This would get me my total velocity. Now, if this is a right angle, I have this side and this side. This should look very, very familiar. You know, this goes back to some base geometry we've done. If I have a right triangle, if I have a right angle here, the side opposite that, that's my hypotenuse, okay? So my v total, I'm looking for the hypotenuse for this triangle when I've added my two vector velocities here. So to find that, Pythagorean's theorem says that the hypotenuse squared, or c squared, is equal to the length of one side squared plus the length of the other side squared. I'm not going to put any numbers in yet. In physics, I would say it's really important to start working on a scale where we're essentially getting our variables by themselves before we put numbers in. So if I'm looking for the hypotenuse, if I'm looking for c, most of my work's already done. I just got to get rid of this squared here. I need to not raise it to the power of 2. So to do that, I needed to do the opposite of that. So the opposite of squaring something is square rooting it. And when I do that, I get c by itself. But now I'm going to put a squared plus b squared in parentheses underneath that square root sign. All right, so I'm going to go, first thing I'm going to do is I'm going to figure out what a squared plus b squared is. That's pretty easy for me to do on my simple calculator here. It's not that advanced. If you have your own graphing calculator, it can handle all this math in one go. I still suggest writing out the steps so you know what math has been done. So in this case, I'm just going to say a is 3.7. So I'm going to go opening parentheses, 3.7. For me, my squared button's right here. Plus my b, which is 2.6. Once again, we need to square that. Now, according to this, I still need one more closing parentheses. Hit that. It equals, so it looks like that. I'm going to take the square root of 20.45. I'm not going to round quite yet. I'm going to round, at the end here. So when I take the square root of that, let's see if I can figure that out here. I'm going to go shift here. I hit that. I hit 2. I hit equals. All right. So on this one, my calculator, if you have a Texas Instruments or Casio, this is way easier. But now I get 4.522. I'm ready to round at this point. Let's just call that 4.5. In this case, we're looking at meters per second. I should have added that in. These are meters per second here. Once they get multiplied or squared and then square rooted, we still end with meters per second. We'll go through that later on. I'm going to go back to the purple. So my V total here is 4.5 meters per second. Now, though, there's kind of an important question. I know what the value for my total velocity is. My total velocity to go from where I started here. My velocity to go from here to there. Imagine that's a straight line. My total velocity was 4.5 meters per second. I actually moved. My velocity was actually more than either of these two, which is kind of impressive. By going 3.7 meters per second, 2.6 meters per second, I was actually able to go 4.5 meters per second using Pythagorean's theorem. But the last piece of information I need to know is, what angle is that velocity at? So I have a right degree here, right angle here, right degree. I have an unknown angle I need to know. I know all three sides. I could do some geometry proofs like side angle side, side angle, I could go through and do any of those proofs. Or we could use a much better tool. We could use trigonometry. For those of you that have had trigonometry, I'm sure your favorite mnemonic ever was SOHCAHTOA. For trig, even when you get into like calculus and stuff, this mnemonic here, pretty important. Really what this says is sine. The sine tells you what the ratio of your opposite side over your hypotenuse is. The ca tells us that cosine is adjacent over hypotenuse, so the ratio of these two sides. And then tangent tells us the ratio of the opposite side over the adjacent side. So no hypotenuse involved in all with tangent. Using one of these, we can figure out what this angle is. And since we know all three sides, I can do either one. I can either do sine, or I should say, I could do the opposite of sine to figure out what that angle is. You use sine when you know the degree. You use opposite of sine, or the inverse of sine, when we want to figure out the angle. Sine when you know the angle, inverse of sine when you need to find the angle. So with that, personally, I like tangent. I like comparing the two values we started off with. So now to find that angle, all we're going to do, so theta, all I'm going to do that is I'm just going to take the inverse tangent of, and I'm going to put a parentheses here, I got to do a little bit of math, the opposite side. So if I'm looking for, I know I'm mixing up my colors here, if I'm looking for that angle, the opposite side is 2.6. I'll even put the meters per second. Over the adjacent side, so the side right next to it that's not a hypotenuse is 3.7. Alright, so now, and that's going to get me what that angle is. The other thing you could do is you could take, you can switch these two things around in order to find the angle as well. Sorry, if you know the angle to find either of the sides, do some algebra. But I'm getting ahead of myself. Let's just work with what we have. I just want to know what that angle is. So in this case, calculator up. So I need to find my inverse tangent. So I've shifted. A lot of times it's going to be second and the tan function. So I'm going to do, nope, that's not right. Let's go with that. Opening parentheses, 2.6. divided by 3.7. I'm going to close parentheses on that. Now I'm going to hit inverse tangent, and that tells me this angle right here is 35, let's just go 35 degrees. So this angle here, 35 degrees. And I can even see my V total, if I want to give all the information I have about it, is 4.5 meters per second at a positive 35 degrees, above the X value. So that tells me what my total velocity is, So all that work, 2 dimensions. From working with velocity in 2 dimensions, here's a big takeaway. You need to know what's the quantity, what's the value for that vector, and what angle is it at. So we're going to leave it there. Happy practicing. We're going to make this way more complicated, but it's also kind of fun. So good luck.